Hi, my name is Jin Lin. Today I'm going to present about process screening and process economics and evaluation.
Hi, my name is Fariza, and today I'm going to present on problem statement, objective, and also process flow diagram before and after heat integration.
Hi, I am Khairul Imran. For this presentation, I will present about the basic control strategies, the hazard and operability, which is the hazard analysis, and lastly, the conclusion.
Hi, my name is Lalita, and today I'll be presenting about the wastewater treatment.
Assalamualaikum and hi, my name is Zahirul Hady, and today I will present the part for plant layout and water treatment.
So we are from Group 3 and today we're going to talk about the design of ammonium sulfate and methanol production plant. And then here is the presentation outline.
Okay, thank you, Jin Lin. Now we move on to problem statement and objective. It is commonly known that CO2 and SO2 are the main pollutants in the flue gas. Besides, these gases are also commonly found as a product of combustion, especially combustion of natural gas and coal from refineries. Since the emission of these gases have led to a great impact to the environment, such as global warming and acid rains, its removal or reduction has become a very crucial issue in most of the chemical industries. Not only that, CHA 2014 also has enforced much more stringent emission standard of air pollutant from industrial activities in order to provide better means in ensuring sustainable air quality management. Therefore, the emission of the flue gas must comply to the emission limits and concentration according to CHA 2014. Below are the limits, in which for CO2, there is no specific limit, while for SO2, the limit is set at 600 mg per meter cube. However, the current existing thermal oxidizer is found to emit the CO2 and SO2 more than it is allowed by CHA 2014. So the objective of this project is actually to remove SO2 and CO2 emission from the flue gas, complying to CHA 2014 as well as to produce two value-added products.
Thank you, Fariza, for the introduction. So now I would like to talk about the process screening, which includes the brief process description, the reactor optimization, and the separation system. So the two value-added products that have been proposed in this project is ammonium sulfate and methanol. So there are two alternatives that we have looked into, in which there are alternative 1 and also alternative 2. So what makes these two alternatives different is the method used to produce methanol. For the first alternative, it uses syngas from SMR and DMR to produce the methanol, while for the second alternative, it uses the direct hydrogenation method. So moving next, I'm going to explain briefly about each processes. So here is the ammonia scrubbing, which consists of an absorber, hydrocyclone, and also a dryer. So this is a flue gas desulfurization system that uses aqueous ammonia as the sorbent and then generate ammonium sulfate as the byproduct. So here we have the CO2 purification, which also mainly consists of an absorber and also a regenerator. At here we uses the diisopropylene, also known as DIPA, as the absorbent to purify the CO2. Next, here we have the dry methane reforming, which is also known as DMR. So this is an endothermic reaction in which CH4 will react with the CO2 to produce syngas, which consists of CO and H2. And here we have the steam methane reforming, or also known as SMR. This is also an endothermic reaction and produces syngas, but it involves the reaction between the CH4 and hot steam. So here is the methanol synthesis, in which the syngas that is produced from the SMR and DMR reaction is then fed into the methanol reactor under high pressure and temperature in the presence of catalysts to produce the methanol. And here is also the methanol synthesis, but the methanol is produced from direct hydrogenation, in which the methanol is synthesized by the reaction between CO2 and also H2 under high pressure and temperature, and also in the presence of the catalyst. So how do we actually select the alternative? Here is a preliminary economic potential evaluation that we have done, and as we can see that alternative 1 has higher EP1 and higher EP2 compared to alternative 2. So based on the preliminary economic potential evaluation, we have selected alternative 1 as our process route. So now I'd like to talk about the methanol reactor optimization. So the type of the methanol reactor that have been proposed in this design is isothermal packed bed reactor. It is a water-cooled tubular reactor in which the reaction takes place in the tubes filled with catalyst. The temperature of the reactor can be easily maintained by cooling indirectly to not dilute the reaction gas, and the temperature limitation for this reactor is from 220 to 300 degrees C. Moving on next is the separation system. So basically in our project, we have three important separation systems, which are the SO2 absorber, CO2 absorber, and also methanol distillation column. So first we have the SO2 absorber, which is to separate the SO2 from the flue gas. The temperature for this column is 50 degrees C and pressure of 170 kPa. And here we have the CO2 absorber, which is to separate the CO2 from the flue gas. The temperature for this column is 78.9 degrees C and pressure of 2970 kPa. And finally here we have the distillation column, which is to separate the methanol from the water. The temperature for this column is 84.7 degrees C and pressure of 200 kPa.
Okay, now we move on to heat integration part. Okay, so here is the process flow diagram before the heat integration. And this is how it looked like after the heat integration, in which in this project, the heat integration is focused on two parts. The first one is CO2 purification. To be specific, it will be focused on exchanger 202. And for the second part, around dry methane reforming. To be specific, on exchanger E301. Okay, in this part, heat cascade diagram, composite curve, and minimum heating and cooling requirement will be further discussed. As we know, a minimum heat transfer driving force must always be allowed for a feasible heat transfer design. Therefore, a minimum temperature difference delta T min is set to be 10 degrees Celsius. Based on the heat cascade diagram that is obtained from HINT software, it can be observed that the pinch temperature is at 353.49 Kelvin, giving the minimum heating requirement around 33,700 kilowatt and the minimum cooling requirement around 51,800 kilowatt. While from the composite curve for CO2 purification process, the heat flow of the process is demonstrated by showing the temperature difference between hot stream and the cold stream, as indicated by the red and the blue line respectively. From this diagram, the hot and the cold utilities are placed as indicated, and as we can see, the amount of the hot and the cold utilities required favored the amount of minimum heating and cooling requirement. Okay, moving on to the MR. It can be observed from the cascade diagram that the pinch occurred at approximately 1200 Kelvin, giving the minimum heating requirement of 0 kilowatt and the minimum cooling requirement around 27,700 kilowatt. While from the composite curve for the MR process, the same as CO2 purification, where the heat flow of the process is demonstrated by showing the temperature difference between the hot stream and the cold stream, as indicated by the red and the blue line, of course. Okay, from this diagram, only cold utilities is required, since there is no minimum heating requirement and the cold utility is placed as indicated in the figure. Lastly, we can also see that the amount of cold utilities required actually favored the amount of cooling requirement. Okay, in summary, after the heat integration, there are 3 total utilities, 1 hot utility and 2 cold utility. Not only that, it can also be seen that there is huge reduction in hot utility, which is from around 146,000 kilowatt to approximately 33,000 kilowatt, leading to 76.90% reduction. While for the cold utility, there is reduction from around 192,000 kilowatt to approximately 76,000 kilowatt, giving 58.56% reduction. Okay, that's all from me. Now I pass to Imran. Thank you.
Thank you, Ms. Fariza, for the heat integration part. So now let's moving to the next section, which is the basic control strategies. There are 4 basic control strategies that we are using for our project. The controller are feedback controller, cascade controller, ratio controller, and lastly is split range controller. Each of the controller have their basic working principles stated here, but the purpose is the same, which is to drive the control variable to its desired set point. We will have a look on how each of the controller works through example of a unit process. We apply feedback controller on our compressor, cooler, and heater. We will have a look on how feedback controller works on this process unit. Have a look on compressor. The control variable, which is what we want to control, is the pressure of the stream by manipulating the speed of motor. From this figure, we can see that the reading is taken after the process unit and a signal is sent to the motor of the compressor to adjust its speed until desired pressure in the stream is achieved. Same goes to cooler and heater, where temperature of the stream is taken after the process unit and the utilities is adjusted until the desired set point is achieved. Feedback controller also applied to our distillation column to control the temperature, the pressure, and level of the column. Next controller is cascade controller, where it is applied in our absorption column and methanol reactor. Cascade controller consists of 2 controllers working together, which is one is primary controller and another one is slave controller. Primary controller will send signal to slave controller, while slave controller will send signal to control unit to adjust moving towards desired set point. For example, level controller will read the level inside the absorption column and send signal to slave controller, which is flow controller. Flow controller sends signal to valve to be adjusted toward desired set point. Same working principle applied in the methanol reactor to control the temperature. The third controller will be the ratio controller. Ratio controller is one type of feed-forward controller which measures disturbance in a stream and help the ratio at desired set point by controlling the other stream. This controller is applied to the feed inlet to our DMR reactor. As the flow rate of carbon dioxide is unstable, it acts as disturbance. Ratio controller will measure disturbance in carbon dioxide stream, and ratio is maintained at desired set point by controlling the flow of the methane. The last control strategy applied in our design is split range controller. The controller involves 2 streams, where a single controller is employed to control 2 final streams. For example, in our flash system, we want to control the pressure of the flash drum by monitor the flow rate of the gas. If an abnormal occurs where the pressure in the flash drum is increased, the controller will send signal to 2 valves, which the valve for the normal operation to be shut and valve to the flash system to open. The excess pressure will be vent through the flash system. This is our complete PID. The next section of this presentation will be the HAZOP and operability HAZOP. For this part, we will look into how to operate 3 nodes in our plant design. We will look into one different example parameter for each node in our next slide. The first node for HAZOP is the methanol reactor, where the synthesis of methanol takes place. So the parameter that we will look into is flow. The flow can be no or less or more. So the possible cause for no or less flow is CV505 failure to open during normal operation. The consequence for that is no feed to the reactor, causing no reaction to occur, and also surging pressure of K501 causing compressor failure. So the safeguard for this is make availability of bypass. For more flow, the possible cause will be CV505 failure to close during normal operation. This will cause the overloading of feed to R501. So the safeguard will be the install high flow alarm. The recommendation for this is regular inspection and maintenance. So the second node for HAZOP is methanol distillation column. So distillation column is used to separate methanol from moisture. So the parameter that we will look into is temperature. Temperature can be less or more. So the possible cause for less temperature is CV522 failure and start close during normal operation. This will cause pressure drop in C501. For more temperature, the possible cause will be CV522 failure and stuck open during normal operation. This will cause overheating of C501, causing pressure build-up inside C501. Other than that, the possible cause for more temperature is E507 motor is damaged. This can cause inefficient cooling duty by E507, causing pressure build-up at the downstream. So, for the safeguard for this is to install temperature indicator and controller. So, recommendation for less temperature is high temperature alarm system need to be installed. Check maintenance procedure and schedule. So for more temperature, the recommendation are low temperature alarm system need to be installed, check maintenance procedure and schedule, and lastly, proper inspection and maintenance of the motor. These are HAZOP for node 2. The parameter is pressure and also level. The last node for HAZOP is absorption column. So absorption column is used to separate CO2 from other components. The parameter that we will look into is level. The level also can be less or more. For less, the possible cause is V201 failure and stuck open during normal operation. This can cause pressure build-up in C201 causing tray collapse. So the recommendation for this is low level alarm system need to be installed and check maintenance procedure and schedule. So for more level in the absorption column is V201 failure and stop close during normal operation. This can cause C201 flooding causing tray collapse. It also can cause quality issues. So the recommendation for this is high level alarm system need to be installed and also check maintenance procedure and schedule. For the safeguard for both less and more level for absorption column is install level indicator and controller. This is HAZOP of node 3 for pressure parameter.
Thank you, Imran, for your HAZOP presentation. Now I will proceed with the plant layout. Plant layout consists of two main areas, which is the process area and the non-process area. For the non-process area, this area has the least potential hazard for workers, and the area should be located at the distance of at least 60 meters away from the process area. The non-process area mainly consists of the administrative building, which, for example, are the Technical Service Department, Main Lab, HSE Department, and many more. Move on to the process area. This area are where the process building, storage, and equipment are located. It is the heart of the plant and is the most hazardous area since it deals with a lot of chemical and reaction. For example, the buildings and unit at the process area are analysis laboratory, methanol synthesis area, water treatment plant, and many more. Besides, there are areas such as expansion ground for future plant expansion. Moreover, there are also assembly points in which all personnel will gather in the case of emergency and unsafe incidents. That's all for the plant layout part. Now I will proceed with the waste treatment. As we all know, waste treatment is one of the most important steps in plant design, as this is to ensure all waste are managed systematically before releasing it. The wastewater usually contain of unreacted reactant left over by product from reaction of the plant. There are two types of waste that are identified from our plant, which is the waste from liquid phase and the waste from gas out phase, which are mainly consist of carbon dioxide, sulfur dioxide, carbon monoxide, nitrogen, and many more. There are three origins of waste from our plant, which are the knockout drum, hydroclone, and methanol distillation column, and the total amount of waste identified are 25,989.21 meter cube per day for our plant. Wastewater plant are under the Environmental Quality Act EQA 1974. Waste treatment are regulated by two main regulations, namely Environmental Quality Schedule Waste Regulation 2005 and the Environmental Quality Sewage and Industrial Effluent Regulation 2009. For the Schedule Waste Regulation, the objective for this regulation are to ensure proper management of scheduled waste, to prevent pollution of scheduled waste into the environment, and to monitor the movement of scheduled waste. The scheduled waste can be divided into the 5 parts as shown in the slide. Next is the Environmental Quality, Sewage and Industrial Effluent Regulation 2009. By regulating this discharge will protect the receiving water body and correspond aquatic ecosystem. It also will protect public health from damaging effects of untreated sewage. The concentration and condition for discharge of industrial effluent or mixed effluent should not exceed the limit according to the Standard A or Standard B as shown in the slide. Standard A are the effluent that discharge upstream of water supply, whereas Standard B are the effluent that discharge downstream of water supply.
Now, we will look into the appropriate method of wastewater treatment. The wastewater treatment strategy is divided into 4 categories, which are the pre-treatment, primary treatment, secondary and tertiary treatment. Under the pre-treatment, it is divided into 2 steps, which is the screening and equalization tank. The main purpose of screening is to reduce debris that can disrupt the operation and to protect the valves and pump. The equalization tank function is to avoid equipment disruption and to avoid solid deposition. The figure in the slides shows the screening process unit. Primary treatment comprises of the pH adjustment tank, coagulation flocculation tank, and the DAF clarifier. The pH adjustment tank is to ensure safe pH operation. The pH range of 6 to 9.5 is standardized according to the regulation limit. If the pH is too high, acid will be added, and if the pH is too low, caustic will be added to neutralize the pH. The function of the coagulation tank is to coagulate the particles by adding metal coagulant such as ferric chloride or ammonium sulfate. The flocculation tank is to increase the size of microfloc. To improve the settling, polymers will be added to strengthen the bind. Dissolved air flotation DAF clarifier is to separate solid and liquid from the wastewater. As can be seen from the slide, is an example of a DAF clarifier. Moving on to the secondary treatment process, we have the neutralization tank to adjust the pH and the activated sludge as shown in the figures. In the activated sludge, microorganisms and wastewater are agitated and aerated. Energy is supplied to provide oxygen and to keep the system in an aerobic state. Dewatering process is also done to reduce the mass and volume. And the last stage is the tertiary treatment. It comprises of the filtration process and the ion exchange tank. In the ion exchange tank, the purpose is to remove dissolved ions to reduce the hardness of the water, so we will be reducing magnesium and calcium ions. In the filtration, suspended solids are filtered out and the treated effluent will be released into the water body. To look back, the overall basic flow diagram has shown. Initially, influent will pass through the screening point. After passing through the screening point, it goes into the equalization tank and to the coagulation flocculation tank, where the chemical dosing, such as like the metal coagulant has mentioned before, like ferric chloride, will be added. Moving on to the primary settling tank. From the primary settling tank, it moves to the DAF clarifier and filtration to disposal. However, from the activated sludge, DAF clarifier and the filtration, the recycled water will be recycled back into the equalization tank to undergo process treatment again. From the primary settling tank, it moves to the neutralization tank, to the activated sludge, reverse osmosis and ion exchange softening, and finally the deaerator. And it will be discharged at the final discharge point to be discharged into the water body. Thank you.
So thank you Zahirul and Lalita for the waste treatment part. So right now I would like to talk about the process economics and evaluation, which I will include the CAPEX, OPEX, economic analysis, the rate of return, the payback period, the net present worth, and also the DCFRR. So now let's look at the capital expenditure, which is the CAPEX, and here we have all the equipment that we use in our plant, and from here we can see that the total purchase cost of equipment, which is the total PCE, is about 134 million ringgit Malaysia. So moving on, next is the physical plant cost, the PPC, which is the plant construction cost in addition to the PCE. So the PPC for this project is about 454 million ringgit Malaysia. And for the fixed capital investment, which is the FCI, it is about 659 million ringgit Malaysia. And the working capital, which is assumed to be 15% of the FCI, is about 99 million ringgit Malaysia. So the total capex for this project is about 757 million ringgit Malaysia. So now I would like to talk about the operating expenditure, which is the OPEX. So basically OPEX can be divided into fixed operating costs, variable operating costs, and general expenses. So the total OPEX for this project is about 1.6 billion ringgit Malaysia. Moving on, next is the economic analysis. The total annual revenue by selling the two value-added products, which are the ammonium sulfate and methanol, is about 2.1 billion ringgit Malaysia per year. Hence, the gross income can then be calculated by subtracting the total annual revenue with the OPEX. And the gross income for this project is about 535 million ringgit Malaysia per year. And as for the economic potential, the EP1 for this project is about 927 million ringgit Malaysia per year. EP2 is 861 million ringgit Malaysia per year, and EP3 is about 854 million ringgit Malaysia per year. Now I'd like to talk about the economic evaluation. But before that, let me introduce some of the important assumptions used for this project. First, the plant has life period of 15 years. The construction period of the plant is 3 years prior to the production startup. So therefore, the total investment cost is focused on the first 3 years. And the plant annual operational hour is 8,000 hours. The annual revenue is 50% in the first year, 75% in the second year, and 100% for the subsequent year. And the minimum attractive rate of return, the MARR for this project is assumed to be 15%. So here is the cumulative cash flow table, and as we can see, the cumulative cash flow for this project is about 4.2 billion ringgit Malaysia, and the payback period is 5 years, as we can see from this cash flow diagram. And to calculate the rate of return, the ROR, it can be calculated by using this formula, and the ROR for this project is 37%, which is greater than the MARR at 15%. So this project is a profitable project. So now I'd like to talk about the net present worth, which is the NPW. It is the difference between the present cash inflow and the present cash outflow over a period of time. So as we can see from here, the NPW for this project is about 1.3 billion ringgit Malaysia with 10% as the baseline rate. Next is the discounted cash flow rate of return, which is the DCFRR. So DCFRR is to determine the interest rate at which the cumulative NPW at the end of the project is 0. So the method I use here is the GoSeek function from the Excel. So as we can see from here, the cumulative NPW at the end of project is 0 with DCFRR of 24%, which is also greater than the MARR at 15%. So now I would like to summarize the economic evaluation that I presented earlier. Here we have all the costs for the ammonium sulfate methanol production plant. So the upper part here we have the total revenue and salvage value, and for the bottom part we have total expenses, depreciation cost, investment cost, and also the income tax. So generally, the rate of return for this project is 37%, which is greater than MARR at 15%. The payback period is 5 years, and the net present worth at 10% for this project is about 1.3 billion ringgit Malaysia, and the DCFRR is 24%, which is also greater than the MARR at 15%.
Thank you, Ms. Jin Lin. Based on our presentation today, we choose alternative 1 as from alternative 1, we can meet the car requirement, we are able to get positive gross income, and it is feasible. The total production will be 142,792.5 kg per hour with purity of 99% of methanol and 4,149.43 kg per hour for ammonium sulfate. Through optimization of heat integration, we are able to save 76.9% of hot utility and 58.56% for cold utility. Based on the economic analysis, the gross income is calculated to be 534,737,622 ringgit 6 cents per year, with rate of return to be 37% with payback period of 5 years. The ROR is higher compared to the minimum attractive rate of return, which make this project worth to be done. In conclusion, the objectives is achieved where we are able to construct PFD and PID for this project, hazard analysis and waste treatment performed for this project. Overall, this project is economically feasible. That's all from us for this presentation. Thank you.